Welcome, one and all. We're here to discuss those monochromatic marvels, those coherent curiosities, yes, lasers. Lasers are beams of photons, which are little packets of light waves, which are completely monochromatic, that is, all have the same wavelength, and coherent, that is, they're all in phase. Lasers were first created in 1960, so they're by no means a new technology, but their inner workings are a sad, unknowable mystery. That is all. Not! Seriously though, let's talk about some laser physics. Laser stands for light amplification by stimulated emission of radiation. What does that mean, you might ask? Well, let's start by looking at the atom. Electrons orbit the nucleus at different specific energy levels. As it turns out, we can bump an electron to from a lower energy level up to a higher one by shooting a photon with enough energy at it. Like so. Photon granola.
That was great. Now I'm full of energy.
Now we can push him off his higher energy state with another photon, like this. You might have noticed that, although we only threw one photon at Matt, he threw two photons away. That second photon is conservation of energy in action. It's where the difference in energy between the high energy state and the low energy state goes when Matt drops down. And guess what? That second photon has exactly the same wavelength and is exactly in phase with the first one. Sound familiar? We just amplified light by stimulated emission. Two photons might not seem like much to you, but what if those two went to knock down two more excited electrons? And then those four photons did the same. Pretty soon you got a pretty powerful monochromatic coherent beam now, don't you? As it turns out, you need to work with at least 3 energy levels for the electron to make the laser work. Otherwise, you can't pump up your medium to an excited state faster than it falls down to a lower one. It's like filling a tub with the drain unplugged, or fighting the Hydra. Working with 3 or more levels, however, allows you to get your medium in an excited state faster than it drops down to a lower energy. Finally, a working laser needs an optical cavity to concentrate the light. In this cavity, we can have 2 mirrors at opposite ends, so a single photon can bounce around endlessly until it hits an electron to knock down to a lower energy state. Generally, one of these mirrors will only be partially reflective. What this means is that most of the time, any laser will be reflected off the mirror, but just a little bit of light will leak out, letting the laser beam out of the laser and into the wide world, where it can read our CDs or incinerate our enemies, although the latter would take a hell of a power source. Okay, how do I stop? Lasers come in all shapes and sizes. There are lasers with gas mediums and one with crystal mediums. Those are called solid-state lasers. And of course the infamous Death Star laser that destroyed the planet Alderaan. Anyway, to make a long story short, as long as you have a medium, a power source to excite the medium, and an optical cavity, we can laze away.
What do we use laser for?
If you write with some glue and press powder onto the paper, you get the pattern you just wrote. Laser printer is that simple in principle. The magical glue used here is the laser. Imagine I cut open a laser printer and put a cross-section here. The cylindrical drum in the middle has a total positive charge. It also acts as a photoreceptor here, as it can be discharged by photons. As it revolves, the printer shines a tiny laser beam across the surface to discharge certain points. This way, the laser draws the letters to be printed as a pattern of electrical charges, an electrostatic image. The system can also work with charges reversed, that is a positive image on a negative background. Once the pattern's set, the printer coats the drum with positively charged toner, a fine black powder. Since it has a positive charge, the toner sticks to the negative discharged areas of the drum, but not to the positive charged background. Next, the drum rolls over a sheet of paper, which has been given a negative charge. The charge is stronger than the negative charge of the electrostatic image, so the paper can pull the toner away. Once the toner is transferred onto the paper, the entire drum surface is discharged by a bright discharge lamp. Then the drum passes the charge wire again, which reapplies the positive charge. Of course, in real life, you get the fuser to melt the toner to the paper, and all the mechanical parts involved in the actual mechanism were much more complicated as well. But conceptually, that is all there is to a laser printer. And laser is absolutely the key writing instrument. Here we have a laptop computer. Let's open the CD player. Now you can see there's a tiny lens in my CD player. Laser beam comes out of this lens. How does it know what is stored in the CD? Let's take a look at the CD first. A CD is essentially a piece of polycarbonate plastic. The interesting part is this plastic has bumps on it. Once the clear piece of polycarbonate is formed, a thin reflective aluminum layer is buttered onto the disc, covering the bumps. Then a thin acrylic layer is sprayed over the aluminum to protect it. But I can't see any bumps on my CD. Where are they? You might ask. It's because they're tiny. To read something this small, you need a disc reading mechanism with incredible precision. That's where laser focus comes in. As the laser beam passes through the polycarbonate layer, it gets reflected off the aluminum layer and hits an optoelectronic device. Because the bumps reflect light differently than the lens, the optoelectronic sensor is able to detect a change in reflectivity. While the laser is reading the CD, a drive motor spins the CD. This drive motor is precisely controlled to rotate between 200 and 500 revolutions per minute, depending on which track is being read. Why is it so? Think about the relationship between angular and linear velocity at different radial positions. We also need a micron resolution tracking system to move the laser, so that the laser beam can follow the spiral track. The rest is about electronics, which involves interpretation of the detected changes in reflectivity as digital signal.
Our first demonstration is very simple and shows some of the cool things that you can do with light that is monochromatic and coherent. All you need for this experiment is a laser and a CD. All you do is take the laser and shine it at the reflective side of the CD. Here you can see the green dot on the CD where the beam hits and 4 spots on the wall. This is an example of interference from a diffraction grating. Because light is a wave, it can interfere both constructively and destructively. The microscopic grooves on the surface of the CD make it act like a diffraction grating, so any light that hits it will be reflected off at multiple angles because of the bending caused by diffraction. At the places where the peaks of these light waves coincide, we see bright spots because of constructive interference, and at the places where the peak of one beam and the trough of another coincide, we see nothing because the light interferes destructively. The amount that a diffraction grating bends light depends on the wavelength of the light, so different colored lasers will produce bright spots that are at different angles. This angle also depends on the width of the gaps on the CD. If we zoom in on the brightest spot from the first image, we see that there is also a smaller interference pattern that is perpendicular to the large one because the surface of the CD is more complex than a typical diffraction grating. Our second demonstration is also very simple, but produces results that you may not expect. For this demonstration, all you need is a laser pointer and a strand of hair or very thin wire. Place the hair right in front of the opening of the laser. Be careful not to point the laser near your eyes. Common sense tells us that what we should see is a spot of light with a shadow in the center where the hair is. However, what we actually see is much different. You can see here that there is no central shadow, but there is a line of bright spots running through the center of the laser beam. The light coming out of the laser actually bends around the strand of hair because of diffraction. This means that the light waves are no longer all going in the same direction and can now intersect with one another. In the places where the peaks of the waves intersect, we see bright lines, and where the peaks of some waves intersect with the troughs of other waves, we see the dark spots that you can clearly see in the picture. This line of bright spots appears perpendicular to the direction of the strand of hair because the light waves only bend around the axis of the strand.
In addition to technology, lasers are used in a wide variety of disciplines, such as medicine. For example, lasers are great for destroying tumors because they can cauterize the wound and not have as much collateral damage to other tissues, unlike other treatments such as chemotherapy. This is the National Ignition Facility, where scientists are using 192 lasers to try and recreate the necessary conditions for fusion in stars.
Finally, the beams pass through the final optics assemblies, which convert the original infrared laser light to ultraviolet. The beams then converge on the 10mm target assembly called a hohlraum, generating a bath of X-rays. This causes the tiny target sphere to implode and ignite in a controlled, self-sustaining fusion reaction. The same process that powers the stars.
Lasers are also used for precision measurements. For example, the Apollo astronauts left a mirror on the moon which reflects a laser and can help scientists measure the distance between the Earth and the moon with great accuracy. Lasers can also develop large amounts of energy to very small areas, making them ideal for use on the battlefield. The military is currently developing solid-state mobile lasers for use in warfare.
Lasers are a wonderful part of our everyday lives. They have so many applications, ranging from the civilian, such as reading CDs, to the more interesting, such as causing nuclear fusion. Regardless, I think we can all agree, lasers are pretty cool. All right.